Good afternoon. This is Earth History video lesson for Chapter 6, Part 2, filmed on the same day as Part 1 and on the first day of class after teaching 4 classes. I'm a little tired, but I want to get this one done. All right, here we go. So, basically, second half of Chapter 6. 3 groups of depositional environments: continental, marine, and then in between those two, what we call transitional. Notice they are numbered. We're going to go a little bit out of order. I wanted to save continental for last because it's really cool. Anyway, so we're going to start with the second one, which is transitional, as in between continental and marine. This would include things like deltas. We won't have anything about deltas on my exam for the lecture portion. So what kind of things might we see? Well, barrier islands, beaches, lagoons, which also sometimes just means back barrier marsh. You know, like between a barrier island and the mainland. That's what we mean by a lagoon. Okay, so what kind of things are we going to find there? We're going to find A, beach sands with blanket geometry, the big flat geometry of a beach. B, small dune sands. There goes my phone. Shoot. I should have put it on silent. I'm turning it off. Okay, let's go back to where we were. All right. Transitional environments, small dune sands with crossbeds. As in small, you know, the kind of dunes you find at the beach. They're not as big as the dunes you find in the desert. What else might we find? Fine-grained lagoon deposits, which would include fine sand, but maybe some silt and clay, in other words, mud, with perhaps herringbone crossbeds. Those of you in lab, Dr. Farley may discuss herringbone crossbeds. They're basically really tiny crossbeds. I'm not going to draw them. What else might you find? There in E, there may be coquina limestones, meaning that it's basically sand grains and seashell fragments in a calcite cement. The people that took Earth Science Lab last semester were able to see a coquina limestone. It's the one that looked like a Rice Krispie treat. So you may find coquina limestones from the surf zone. Surf zone, of course, is where the waves break. All right, moving over. We're going to the third topic next, which is marine depositional environments. On your continental shelves, you're going to find sandstones with ripple marks. You might find some coquina limestone. That's technically in the marine environment. You're definitely going to find fossiliferous limestone from your shallow marine environment, and then you might find something called a micrite limestone from an offshore, little bit deeper water environment. And a micrite is basically a lime mud. It's a limestone. It still fizzes in acid, but it's not going to have any fossils. How about the deep sea floor? It will mostly be chalk, which is calcium carbonate, calcite, shells of little coccoliths, and then chert, and chert is basically silica quartz, and it's the remains of little tiny diatoms and radiolarians that made their shells out of quartz, and it makes chert. Again, people that took Earth Science Lab last semester saw chalk and chert. And then another little tidbit here on the continental shelf, it will likely have turbidite. Oh, that says turbite. It should say turbidite deposits, meaning your underwater landslide deposits. In other words, your graded beds. Those are some things that you also might find in the continental shelf deposits from long ago, preserved in the rock record today. Okay, now we're going to move on to the first of these depositional environments, continental. This had the most stuff, so I saved it for last. Okay, in your braided streams, which are mountain streams, where you have a lot of sediment and the water's not all that deep, and you have these big braids of sediment. That's why they're called braided streams. What are you going to find? You're going to find an Arkose sandstone, which is not just quartz. A beach sandstone is usually just quartz. And Arkose sandstone, as in mountains, close to the mountains, you're going to find some feldspar in it as well. People in lab last semester got to see the Arkose sandstone. What else might you find? Conglomerate, which is a poorly sorted sedimentary rock with rounded pebbles. You might also find possibly some cross-bedded current ripple marks. Remember, your current ripple marks, asymmetrical, water going one direction. And you might find some point bar deposits as you're coming down off the mountains. How about in an alluvial fan? What is an alluvial fan? Well, if we were here 3 days a week, I'd eventually show you guys a picture of this on the PowerPoint, but I don't think that's going to happen. Imagine mountains, like steep mountains, okay, not the Appalachians, but mountains out west. Particularly higher elevations. When your rock debris has weathered out of the bedrock there in the mountains, and all it did was spill down the sides of the rock, it hasn't really gotten anywhere. That's an alluvial fan. You could always just do a Google Images search and look at alluvial fans. They're kind of cool to look at. What kind of rock are we going to find there? Breccia, which is poorly sorted sedimentary rock with angular grains, meaning they haven't been rounded yet in the rivers and streams. Okay, now we're kind of moving down into our more flat areas where we would find meandering rivers and streams. What kind of rocks are we going to find from meandering rivers and streams of the past? We're going to find shale, siltstone, in other words, your smaller grain sizes that might easier to be transported in these meandering rivers and streams. You might find shoestring sandstones, real skinny ones that were from point bars or sandbars in this meandering river. And you may have some cross-bedding. You also should have current ripples here. I didn't write it down for the meandering rivers and streams, but I'm going to mention it. Rivers and streams, wherever they are, be it mountains or flat, you can find the current ripple marks, so the ones that are asymmetric. All right, moving on. So close to being done for the day. Okay, how about our deserts? Deserts from the past, you're going to find large cross-bedded sandstones like you might find at Zion National Park out west. You also would find rock salt, also known as salt flats, just big halite deposits, and gypsum flats. Okay, so rock salt and gypsum are evaporite minerals, and those show us an arid environment from the past and some kind of lake that dried up and left behind these minerals. Okay, how about in our glacial areas, like in our tall mountains where you have glaciers year-round? You find something called glacial till. It is likely unconsolidated. I'm not going to say it's impossible for glacial till to become lithified into solid rock, but every glacial till I've ever seen, pictures of at least, was unconsolidated. But it's the most poorly sorted material you will ever see. Very poorly sorted with angular grains. Okay, just a quick snippet here on kind of tying up all these depositional environments. The notion of paleogeography. In the PowerPoints for various chapters, not just in chapter 6, but I think some other chapters later on, what you can do is if enough people have studied a continent or parts of a continent, that you can make these larger maps where you're mapping out the material, the sediments and rock that show you what kind of depositional environment she had in the past. That basically can give you an idea of the geography and climate conditions of that continent in the past. Moving over another board. Okay, kind of a new topic here, sedimentary facies. A distinct body of sediment or sedimentary rock with distinctive physical, chemical, and biological characteristics. In other words, it's its own thing. This is clearly a delta deposit. It's not exactly like anything that is to the east or west or north or south of this delta deposit. All right, that moves on to that second part there. So this distinctive body of sediment or sedimentary rock that is deposited in a depositional environment, like say a delta, alongside sediments deposited in a different environment. In other words, if you're looking at an ancient shoreline, you're going to have different sedimentary facies. You might have a sedimentary facies that is the beach of the past or the barrier islands of the past. A sedimentary facies that is a delta that was there once upon a time, and a different sedimentary facies that is the shallow marine offshore. people in the Earth History Lab. I'm sure Dr. Farley is going to talk about sedimentary facies in his lab. All right, next topic, different color. Marine transgression. This is a sea level rise. Oceans rising like they're doing today. This is going to mean that the shoreline is going to migrate landward. Why does this happen? Well, it happens during a warming period, coming out of an ice age, or humans adding to that and warming the environment. This is due to glaciers on land melting and adding water to the oceans. It's also due to the thermal expansion of seawater. As the sea surface temperatures rise, the molecules of water there close to the surface are actually going to expand. Okay, that actually adds to the volume of material in the oceans. And then fast rates of seafloor spreading, like we saw back in the Cretaceous. We will see in later chapters that during the Cretaceous we did have one of our 6 major transgressions upon North America, and that's part of what was causing it. We had fast rates of seafloor spreading, faster than we see today. How do we recognize, hopefully that'll still focus as I move in closer, how do we recognize a marine transgression in the rock record? Well, you see there a stratigraphy column. You see what's on the bottom, floodplain shale, as in meandering river, like the Cape Fear River or the Mississippi River. Above that, you see a sandstone, which is likely a beach. We'll say that sandstone has blanket geometry. It's a beach. And above that, you have a limestone, fossiliferous limestone, shallow marine, all in the same place. Okay, which of these rocks is the oldest? The one on the bottom, the floodplain shale. Which is the youngest? The limestone. This is what a marine transgression looks like in the rock record. Limestone on top. We have to move to another board, and hopefully since I'm moving around, maybe the lights won't click off. They didn't do it in the last filming, and I'm quite amazed at that, but they did do it when I was putting notes on the board. Okay. How about a marine regression? What is that? It's a sea level fall. This is going to happen during a period of glaciation or glacial maximum. Temperatures cooling, what you might have referred to as ice ages. What's that going to look like in the rock record? Well, our stratigraphy column here, you might see, is opposite of the last one we just looked at. What's on the bottom? The oldest is the limestone. So many years ago, the sea level was higher, and you had limestone being deposited here. And then it started cooling. You start going into the next glacial maximum. Sea level drops off. This is now a beach. Now you got your sandstone beach here, blanket geometry. And then the sea level falls off a little bit more, and your sandy beach migrates seaward, and now you have this meandering river come through, giving you a floodplain shale on top. Again, limestone on the bottom is the oldest, floodplain shale in the top is the youngest. Your limestone's on the bottom here, marine regression. All right, Walter's Law. Okay, important for Dr. Farley's lab, for the 8 or 10 of you that are in Dr. Farley's lab on Wednesday afternoon. What does this say? Well, a facies, sedimentary facies, seen in a conformable vertical sequence, vertical meaning up and down, conformable just meaning that you don't have any unconformities there. Sedimentary facies seen in a conformable vertical sequence will also be found in a lateral sequence. This applies to both marine transgressions and regressions. I have a drawing here to try to mimic what you would see in the textbook in this chapter or the PowerPoint. So on the left is our vertical sequence. Here we have a stratigraphy column showing us a marine transgression, limestone on the top, like we looked at on the other board. And that's equal to what we see on the right. You will not only see the sea level rise in a vertical sequence, but you'll see it in a lateral sequence as well, okay? So what do we have in that drawing on the right? Well, you have the old sea level at the bottom. You have a floodplain shale that used to be there when it was a meandering river. Okay, sea level's starting to rise, okay, and that means that your beach, your sandstone beach, is going to move landward, and that's what you see there. And then the sea level continues to rise because conditions are still getting warmer, and now you have marine water covering what had been a floodplain shale and a sandstone. And the way I've drawn it, the seawater is there. It's not a rock yet. It's a future limestone. But just showing there, you're kind of going from left to right in a lateral sequence. And you see the same thing in the vertical sequence that you see in the lateral sequence. All right, a couple last things here. Okay, something interesting that we'll talk about more in later chapters. Since the late Permian, which is basically the end of the Paleozoic era, before we get the dinosaurs, since the late Permian, there have been 6 major marine transgressions upon North America. We'll learn more about those in later chapters. All right, how about our last topic for Chapter 6, Video Lesson Part 2? Okay, causes of transgressions. Sea level rises. Well, a warming climate. What causes that? I don't know that we'll have time to touch on the Milankovitch cycles in class. I can't remember if I have them on a past PowerPoint or not. So at some point I'll try to briefly mention it in class. Milankovitch cycles have to do with Earth's path around the sun. Sometimes it's more elliptical, sometimes less elliptical. It also has to do with the degree of tilt of Earth's axis, currently 23.44 degrees, but it can vary from as low as 21 degrees to as high as 25 degrees. It also has to do with Earth's wobble, meaning we spin around slowly like a top or a dreidel. And the way our axis currently points, Polaris is the North Star. Everybody knows Polaris is the North Star, right? But something like 12,000 years from now, we will have swung around 180 degrees, and there's a different star that will be the North Star. And I can't remember what star that is. Maybe Vega. I think it's Vega. I think at that time Vega will be the North Star. What else caused the transgressions? Not just change in Earth's tilt, wobble, and path around the sun. Rapid seafloor spreading, and I didn't go into detail on this on the other board. This happened in the Cretaceous. Rapid seafloor spreading means that your mid-ocean ridges, the underwater volcanic mountain ranges, become wider. That topographic high spreads out more, so that means you have less room in your basin for seawater. What else can cause a transgression? Coastal subsidence at the edge of the continent, meaning the edge of a continent on a passive margin sinking. This is also referred to as tectonic subsidence. They talk about that in your textbook at some point. Causes of regressions, or causes of sea level falls. Well, of course, ice ages, glacial maximums. Again, these are also largely caused by Milankovitch cycles. Uplift of continents will lead to some local regressions, local sea level fall, and possibly very slow seafloor spreading. I say possibly and I say very slow because currently our rate of seafloor spreading is pretty slow. But we are not experiencing a regression. We are experiencing a transgression. Why is somebody trying to come in this room? Maybe they're trying to clean it. I'm just going to let it go and hope they walk away and try to finish this video. Anyway, I'll be out of here in like 10 minutes and then they can have this room. So we do currently have pretty slow seafloor spreading. But again, we are experiencing a transgression, not a regression. So I don't necessarily think of slow spreading as a major cause of a regression. All right, guys, that is the end of Chapter 6, Video Lesson Part 2.